Nice of you to join me for example 7.2.1. Here we are asked to let x and y be as in example 7.2.1, that was in the previous video, and then we are asked to calculate the expected value of y two ways. One, using LOTUS, the law of the unconscious statistician, and two, using the density function that we calculated in example 7.2.1 and the definition of expected value. We're asked then to verify that both methods give the same answer. So from example 7.2.1, here's the cumulative distribution function for our variable x. We had that y was equal to x squared, and this is the density function that we calculated for y in the previous example. LOTUS. Let's review what LOTUS says. So it says the following: if we have y as g of x, and so I'm obviously thinking of g of x as x squared that we're going to use here. LOTUS tells us, so the law of the unconscious statistician, tells us that the expected value of y can be calculated entirely through the distribution of x. So that tells us that we can integrate from minus infinity to infinity of g of x times the density, the PDF, of x dx. So notice that we have the expected value of y, but in the integral are only x terms. So the x squared we have here, what we don't have is the density, but we can calculate that from the cumulative distribution function because f sub x, the density, is the derivative of the cumulative distribution function. And since we have the cumulative distribution as 1 minus, if we write this a little bit in a different way, 4 squared gives me 16 over x squared squared, so x to the minus 4 primed. So the constant goes away, the minus 4 comes down, multiplies, I'm going to get 64, positive 64, over x to the fifth. That is the density function, and that's what's going to go in here along with x squared. So now, integrating from minus infinity to infinity because we're 0 below 2 is the same as integrating from 2 to infinity, and we have x squared is the g function times 64 over x to the fifth dx, which, if we clean this up, is 2 to infinity 64, how did I write 65? 64 over x cubed dx. So improper integral, we need to evaluate this as the limit as t goes to infinity of some antiderivative from 2 to t. The antiderivative is here, we've got x cubed, so bump up the power, we're going to have x squared, so that's x to the minus 2, divided by that same minus 2, so 64 divided by minus 2 gives me minus 32. We're going to evaluate this, so the limit as t goes to infinity, fundamental theorem, so I get minus 32 top minus bottom, t squared minus minus plus 32 over 2 squared. This first term goes to 0, and then we have 32 over 4, which is 8. So the expected value of y using LOTUS gives us 8. We're going to go and compare that now with the definition of the expected value. So the second way is the definition. And the definition, the expected value of any random variable, continuous random variable, is the integral from minus infinity to infinity of y times the density function of y. Not dx, but dy. So we have all the information that we need for this because we calculated the density in a previous video. We're going to integrate from 4 to infinity now, as the support dictates, so 4 to infinity of y times, what is this now, 32 over y cubed dy. That can be simplified a little bit, so the integral from 4 to infinity of 32 over y squared dy. Again, we have an improper integral, so the limit as t goes to infinity, the antiderivative, or some antiderivative here, is going to be run from 4 till t. We need an antiderivative here, bump up the power, So we're going to get y to the minus 1, so over y minus, divide by the minus 1, 32. And I think you can see that this exact same value is going to pop out. So we have here the limit as t goes to infinity of minus 32 over t, minus minus is plus 32 over 4. We again get 0 plus 8 or just 8. So these are obviously the same value, and we have done what the question asks, that using either this powerful theorem Lotus or first calculating the density, which we did in a previous video, and using the definition of expected value, we will get the same answer for the expected value of y.